So right now we have Marshall from Texas A&M University. Thank you very much, and you can go ahead and get started.
Thank you. The title of my presentation today is using test positivity rates and reported cases to estimate state-level COVID-19 prevalence in the United States. During the first year of the pandemic, reported cases and test positivity rates were widely used to inform prevalence as well as policies. But we know that these two metrics provide highly biased estimate of disease prevalence. So the objective of our study was to develop a simple semi-empirical model to estimate state-level prevalence of COVID-19 in the US based only on reported cases and test positivity rate. We then developed a model that's based on a number of assumptions. First, we assume that the positivity rate is correlated with a lag undiagnosed prevalence in a population, and that the correlation between these two is a time-dependent function. This time-dependent function here, which we denote as BT, we assume that it is a convex function of the testing rate. And this was also based on a number of assumptions. First, we assume that during the period of interest, at least during which we conducted our study, large-scale passive testing was the baseline testing at the state level in the US. With this assumption, therefore, it unfolds that from such a baseline, an increased testing rate will result in what we call here a diminishing return. We have a bit more explanation about this in our publication, but for the sake of time here. So we denote this function here, BT, as a negative power function of the testing rate. So therefore, using that, we are able here to derive here this very simple expression between undiagnosed prevalence, testing rate, and reported cases, which you then use also to derive a function for undiagnosed seroprevalence as a function of two additional parameters here, which one of them is what we call the initial seroprevalence that was missed before we reach large-scale passive testing. We fitted this model against seroprevalence data, obtained state-level seroprevalence data obtained from CDC and other publication, and validated also a model against those data. And we observe here that for most states, that initial seroprevalence SP0 was less than 1%, a exception of 3 states for which was higher than 5%. And this was consistent with a large surge of cases in those states, as well as a death-to-case ratio that was very large during the early days of the outbreak. Finally, we validated the prediction of this model by comparing it with other mechanistic model that also provided state-level estimate of prevalence in different states in the US at a daily scale, and we show that our model result compare very favorably to that of this mechanistic model. So thank you.
Excellent. Thanks very much, Marshall. So we have a few extra minutes for questions before we move to Deborah's scientific session. So again, if you have any questions, you're welcome to use the chat function, or just a reminder that if you want to use the raise hand function, you can go to the reactions menu at the bottom of your Zoom screen, and the little up arrow will, that's where you can find the raise hand function.
All right, so I have a question. Can you go back to your previous slide?
Yes.
The first slide, I guess, your assumption.
The first one, yes.
So the active testing will increase the infected population testing rate relative to the general population testing rate. Can you just elaborate on that a little bit? Because I wasn't quite sure I understood that assumption.
So basically what we mean is that let's assume that large-scale passive testing is basically what is going on within the community. If you want to increase testing by doing more kind of active testing, for example, testing through contact tracing and other ways, what we are likely to do, we are likely to identify sorry, let me look at it here. What we're likely to do here, we are likely to start identifying less and less cases as we test more and more, because most of the infected cases will have been already been captured through
Got it. Okay.
passive testing. Yeah.
Got it. Thank you.
Thanks, Harry. And also in the chat, Laura's asked a question asking if you could give a little bit more detail on the equations.
Yes.
I guess if you need clarifications from Laura, she can explain, but
yeah, maybe she can explain, that will help.
Yeah, hi, thank you. This is very interesting. So I was wondering if you could go over the equations when you combine them, like,
Okay.
because that's kind of like the meat of your method in a way, correct?
Yes.
Yeah. So if you can please kind of explain that, like that line a little bit better.
Okay. So
I mean, not better, but since you have the time, you know, like more.
Yes. So let me explain this, the first one. The second one, which is about seroprevalence, I'll mostly refer to our publication, because what we did here is that we kind of discretized a bit the time step here to be able to move from prevalence to seroprevalence. So there's a bit more detail here, and it will take a bit longer to explain that here. But what we have here, for example, with the prevalence or undiagnosed prevalence. So here, this equation of undiagnosed prevalence, and basically just some undiagnosed with reported cases to figure out what is the prevalence. So that is how we get to undiagnosed to total prevalence. What we assume here is that the lag undiagnosed prevalence, in other words, if you have a positivity testing rate today, what it basically capture, it is the state of the disease T lag days ago. So what we assume is that if you have positivity rate today, which is a P plus here, we assume that is basically equal to a BT, which is a bias function, which is a bias rate here of the undiagnosed prevalence. So basically that is just what we rewrite here by bringing this B to the power -1, just sending it to the other side. Yes, go ahead.
Sorry. And what else? What is N test? I guess that's not defined.
What is
N test, tau.
Oh, what is
You know,
N?
where you define.
Oh, yes, I see. This N test. Yeah, this is
Yeah.
just the number of tests that is administered in a day, in a given day T. That's just what it is, divided by N, which is a population size. Yes.
Okay. And little n is just some number?
Yes, just some kind of, yes, just some power function, just a kind of a variable that we're going to, a parameter, sorry, that we're going to estimate.
Okay, I see. Thank you.
So, thank you.
great, thanks, Laura. So I'm not seeing any other questions. So thanks again very much, Marshall, for your lightning talk.